Hi, my name is Israel Reimer, and the topic of the research I performed this summer is the diffusion in A15 niobium-310 using UF3 potentials. A bit about me is that I'm majoring in mechanical engineering and physics at the University of West Florida. I plan to graduate on May 2024. I'm working with the SURF program in the Herbert Wertheim College of Engineering. I'm working with the Hennig Research Group in the Material Science and Engineering department. As far as future plans go, I plan to pursue a PhD in material science and engineering in the future. A bit of background and motivation behind this project is NB310 or niobium 310 is a superconductor material that has a high critical temperature and it also has a high critical field. Understanding the grain growth of niobium tin in the internal tin process, which is the manufacturing process that produces the niobium 310 material. Understanding this grain growth and the diffusion mechanisms of tin and niobium is key to be able to produce uniform films and wires and things that can be used in its various applications. Poor diffusion of tin in the process leads to columnar grains and bald spots in films and in wires, and these can exhibit poor superconductive properties, properties such as zero electrical resistance and the expelling magnetic fields when it's cooled to temperature to a critical temperature near 0 degrees Kelvin. Um, Another motivation behind this project is to also validate the ultra-fast force fields or UF3 potential models that were produced by the Hennig group. A few of the requirements in this project were to perform calculations using density functional theorem, DFT, and using the UF3 models to perform molecular dynamics calculations, which are much quicker than DFT calculations, which is the point of creating the UF3 models that reduce the time it takes to compute these calculations. Some of the hardware and software used was the Hypergator supercomputer. That I ran VASP calculations, LAMMPS calculations, as well as produce lattice structures, which you can see to the right in images on the right. I used Vesta to create those and VMD to visualize those. As I said, Vesta was used to create several types of structures with those with green boundaries and those with perfect lattice structure with anywhere from 215 to 10,900 atoms. The procedure of this research was largely inspired by a research paper published by Pohang University of Science and Technology in the Republic of Korea. The UF3 model validation is seen here. The images on the left, the upper image, is the relaxed grain boundary structure that was produced using the UF3 models and molecular dynamics calculations, which is comparable to the to figures A and B on the right that were produced in the paper published by Pohang University. In the bottom of that image on the right, you can see a chart which displays the vacancy formation energy um, with relation to its distance from the grain boundary. And these distances can be seen in figure C, right to the left there, where the grain boundary is the dotted line. The same calculations were ran using UF3 potentials, and the results for which can be seen in the image on the bottom left. You can see that the results don't quite align. The several of the values at different positions went negative, which is not coincident with the results found by other groups. Some more of the results, along with the results from the previous slide, uh, those that implicated that the UF3 model could be improved upon, especially in the calculation of vacancy formation energy. However, the model did perform well in the calculation of grain boundary energy, which can be seen in the table in the upper right on this slide. Its values were in line with results found by other groups that performed similar or the same calculations. Um, Also, the grain boundary diffusion coefficient for niobium and tin were calculated at four different temperatures at 900 Kelvin, 1000 Kelvin, 1500 Kelvin, and 1800 Kelvin. These results can be seen in the table in the bottom right. When these results are compared with the diffusion in bulk or the fusion across the surface or uh, in the volume diffusion, it can be seen that these are much larger in magnitude, indicating that the grain boundary diffusion is the primary diffusion mechanism in niobium 310. I would like to thank a few of the following groups for making this research possible this summer. First being the SURF program, especially Ashley Wilson and Mike Nazareth for organizing seminars and meetings and housing and all of those things. I'd also like to thank Dr. Hinnig for offering me a spot in his research group this summer, as well as Ajinkia, Sam, Eric, and Jason for being my mentors and helping out with any issues, problems, and questions that I had. Thank you.